This year. So that everyone goes down. So that
Alright, I was going to
that was my only question, but I didn't feel that it was really
Easy way to do that.
I'm gonna go do the.
Alright, hey guys, we got 11 o'clock, so let's get started with our second talk. I'm here to introduce Fred. He's a Case alum and Yelp full-time employee. He had an internship at Yelp. I'm sure he'll tell you more about his time at Yelp. And Fred's going to talk about how to scale websites. So Yelp knows something about that, so please. Fred.
How you doing, guys? Did you enjoy John's talk?
Yeah.
Yes.
Got big shoes to fill. Yeah, so I'm Fred. You're probably wondering who the hell am I? I was a Case alum. I joined Yelp. I did an internship at Yelp and joined them full time. I work on their infrastructure team. Primary responsibilities are essentially availability, performance, and productivity. So make sure the website stays up, make sure it stays fast, and make sure that we can keep our other developers productive. So how many people here have used Yelp? So mostly familiar with what it is. It's basically it helps consumers connect with good local businesses, and that that marketing nomenclature translates to basically lets you write reviews about businesses and figure out what the good stuff near you is. So I'm going to talk about what Yelp is, what our back end looks like and how we scaled it, how we accelerate content delivery on the front end, and how we manage to monitor the performance of an increasingly complex system. So, as I mentioned, this is Yelp. Our stats as of Q2 of this year was basically 78 million monthly unique visitors, and we're growing on 30 million reviews, and we've got a nice sort of upward growth trend, which presents all sorts of interesting engineering challenges. So Yelp paid for my plane ticket here, so I would be remiss not to do a little bit of a recruiting spiel, in case you didn't get enough from the previous talk. Yelp, this is basically it. Yelp is all about finding the good stuff near you. We're recruiting full-time and interns. There were lots of parties. You may or may not have heard of Yelp hires community managers that are essentially responsible for throwing parties in every city. So you should keep an eye out. I know we've got one in Cleveland that
the greater
is fairly active. Yeah. So on the technical side, what is Yelp? There's sort of 5 main websites. We've got the website, which is the consumer-facing website, what most of you have probably used on a laptop or a desktop computer. Biz site, which is for geared toward business owners. It lets them go and manage their business page, go and buy advertising, see metrics about who's visiting their business page and how frequently. API, which has our public and private APIs. It also powers our mobile app. m.yelp.com, which is a mobile website, which if you use it on a phone and go to yelp.com and Safari or whatever web browser you've got, it'll take you to our mobile app-like website, and admin.yelp.com, which is when everything's going wrong, the site helps you make it right. We are in a bunch of different countries. I think it's like 16 different countries at this point, and growing quickly internationally. We also have numerous open source projects. I think our highest profile one is probably called MRJob. It's a Python MapReduce framework, which if anybody's used MapReduce here, the classic sort of implementation is Hadoop and writing Java jobs and sort of trying to wrangle either EC2 instances or Amazon EMR or managing your own Hadoop cluster, which tends to be a pain in the butt. So MapReduce, or MRJob lets you write MapReduce jobs in Python. It's a nice, easy def map, def reduce. Firefly, which is our front end, it's like our time series performance graphing framework. I'll talk more about that later. Testify, which does it's like a Pythonic unit test framework. It's supposed to be more Pythonic than unit test 2. Tron, which is like a distributed cron implementation, and a bunch more. We've got a GitHub page if you're interested in checking us out. There are going to be a lot of cat pictures in this presentation to give you kind of a small break. If any of you guys have had classes with Tekken, who's a fan of the 1-minute break. I'm also a fan of the 1-minute break. So who here has built a website? Show of hands. Even if it's just a small one for yourself. So you're probably all very familiar with sort of the single server setup. Maybe it's an EC2 instance, maybe it's a box under your bed. Maybe it looks a little bit something like this. Maybe you don't even have Python running, but you installed Apache Nginx. Maybe some Ruby, maybe some Python, a data store. So this is what Yelp looked like on the very first day. Some Python scripts backed by Apache and MySQL for a data store, all running on the same box, happily, able to serve a couple of requests a second, low traffic, kind of a good starting point. Nothing fancy, no load balancing, no internal DNS, no web framework, just us, mod Python, and MySQL. So easy. Life is simple here. Maybe not highest traffic, but no problem. So after a certain point, one web server doesn't really cut it anymore. That'll only get you so far, but you've got a lot of stuff running on the same box, and once if you hit the front page of some social media website, everyone's familiar with the slash dot effect. So time to scale out. Get a load balancer, just simple HA proxy. Drop in load balancing. A couple web servers. The web servers are the easiest to scale out horizontally because you've just got sort of idempotent Python scripts that don't really maintain a lot of state. MySQL is your big state store, so it's really easy to just throw additional hardware at the web server side of things, and that'll get you pretty far. I forgot to mention at the beginning that I've got a bunch of slides here, but I'm more than happy to take questions along the way if something sort of piques your interest. We don't have to rush through this. So yeah, you can add new web servers, but it's easy to scale this horizontally, but you start to reach some limits with this, and you see there's two potential bottlenecks here. HA proxy, which isn't really going to be a bottleneck because it's designed to be really quick, and I think most we run 2 HA proxy instances at this point, but most websites can get by on one for a long time. The bigger problem is the data store. As you can see here, MySQL has a lot of incoming connections from a lot of incoming web servers, and at some point there's just going to be a ton of load on the database, and it's going to be very slow to get results back or to add new content. And if you're running a dynamic website, content is king. Being able to have people responsibly retrieve content and insert content is paramount. So we've got some options. These are some of the classic options that you can consider when you find out that your data store is just too slow. You could find a faster data store. Arguably, there are things that are faster than MySQL, but this isn't really a great option. I mean, you could go into the closed source world and use something like an Oracle database or Microsoft SQL that maybe a salesman told you was faster, and still get relational databases. But we like MySQL. We don't want to sort of change our paradigms. Key value stores, not so much. Yelp is built on a lot of relational data. Users have reviews, and reviews are about businesses. And it's sort of hard to break those things apart. So finding a new data store isn't really a good option. We could just add another database machine. I mean, what could be so hard, right? You just take your schema and you copy it over, and then just sort of write some things to that database and read some things from the first one and read some things from the second one. But that gets really hairy really quickly because then you have to figure out what content is in what database, and it's also not a great option. There's a lot of manual engineering overhead, so we'll nix that one. Sharding. Who here has heard of sharding database? So this is an interesting idea. The classic definition of sharding is basically taking your one database and making it a bunch of databases, and letting MySQL take care of the fact that some data is on some nodes and other data is on other nodes. And this is fine, but you end up needing, if a single shard goes down, then you have the potential for data loss, unless you've got backup somewhere, so you end up needing a bunch of shards to sort of achieve the same reliability. And additionally, this is really great if you have sort of heavy write traffic, because you can just sort of scale up with the number of writes that you need to do. But fortunately, Yelp's traffic pattern is very read heavy. As much as I would like to encourage all of you to go and write reviews and quick tips on businesses and go check into your Starbucks or whatever, the fact is we're very much reads. People show up at Yelp and look for basically looking for content about businesses. So we're going to stick with this last option, which is replication. This is really great for read-heavy traffic, because the idea here with replication is you have a single master database, which is sort of like in the old world, takes all the writes, can do some of the reads, and then you have slaves set up, which sort of replicate these writes and pretty much handle read-only traffic. A cat for you. So the old world, some web servers, a database node does all the reads and writes. We want to make this a little more sustainable. So we'll introduce a simple replication scheme here, which is you have web servers will do all of their writes to a single master database, by database 1, and it will do some of the reads there as well. And then you'll have webs doing reads from a replicated database, and only reads, not writes. And then when you make a write to the master database, it gets replicated through a replication stream out to the read database. So that's at a high level what the idea behind replication is. Yeah.
Do you guys have multiple data centers in like the US or?
Okay, I'll get to that. Yeah, this is a very nice and simple picture, and it gets much hairier from here on out. So one of the first things that people do when they set up replication is they tend to set up basically a second master database, which isn't used for any real traffic, but still has writes replicated to it. This is kind of a good idea because you're introducing, trading off, for this additional capacity, you're introducing kind of a single point of failure, which is if your master database goes down, then you have to promote what could essentially be an out-of-sync slave to be your master, which has the ability to introduce data loss. So you bring in a second database which replicates your writes. Hopefully it's one of the first things in the replication stream, so that if your master database goes down, you can promote in basically a fresh copy. So the thing I kind of glossed over here is that when you replicate writes from a master to a slave, there's time involved. And when you're in the same data center, maybe your machines are in the same rack, mostly negligible. Maybe time to replicate writes under no load or light load is on the order of milliseconds. But we've already reached a condition where we had one database that was succumbing to load. So having a second one, there's going to be presumably some moderate load on each of these databases. Maybe we're doing some reads from one of these read databases, and we have, maybe we have to lock some rows, or maybe there's just additional query capacity and we couldn't get a write through in time. So this has the ability to make your slave nodes somewhat out of sync, and I'll touch a little bit about, this basically introduces a lot of problems. Life is really easy with a single database. And it's not so much anymore, because you're essentially making a trade-off between strong consistency and eventual consistency. Who here has taken a databases class? So for those of you who have, you've probably heard of the cat theorem, right? And a brief summary of the cat theorem is basically, it's kind of like a fundamental thing in computer science. You can't have all three of consistency, availability, and partition tolerance. Did I get all the letters right? Sorry?
Consistency, availability, and partition tolerance.
Cool. So basically you can have two of those things, but you can never have three. And what, the trade-off that we're making here is we're losing some consistency for increased availability, that is additional read slaves, and partition tolerance. So if we have a bunch of nodes go down, we can just sort of spin more up. And if we can't spin up more nodes, we at least have all of our data still available. We haven't lost any data in losing nodes. Strong consistency is nice because you can make sure that basically you always have the same view into the data and there's no surprises for a consumer. But in eventual consistency, you only know that at some point in the glorious future, you'll have all of your data in a single consistent view. But that may not be the case right now. And this exposes a lot of cons. If you have somebody doing a really gross query against your database, it has a little bit of like a multiplicative effect because you have to replicate really bad inserts to all your edge nodes. And if you do a really bad read against the master, for example, or like a select for update, which requires, which tries to lock a whole bunch of rows that can't be changed, that query will also get replicated through the stream if an update happens and sort of lock those same rows on your slaves, making them unreadable by pretty much all of your web traffic. Like I mentioned, it can lead to inconsistent views. And it can be difficult to figure out when I should hit the master versus a slave for a read. I mean, it's easy, we always hit the master for a write, but it's not always trivial to figure out if we need to be hitting the master to try to get a consistent view. So, go into a little bit more on these gross queries. So you've got a normal sort of query stream, queries coming in from the webs, just doing normal application traffic. Maybe you've got a couple quick inserts. Maybe this guy's really nasty and wants to do a table scan and then some sort of update. So the inserts go through fine, get replicated out to the slaves. Everything's hunky-dory, really nice, quick, small queries. But you have this really nasty query coming in to the master database. And the master database gets sad because it needs to reserve a whole lot of stuff, which renders rows and ultimately data unavailable for a short amount of time. And then all of a sudden, that same query, if you don't kill it off quickly enough, will replicate out to your slaves, and you've got angry users wondering why it's taking a page seconds to load, or simply database connections getting killed, and even worse than taking a long time to load, you get errors. You also run into problems with consistency. So let's say we've got a user, let's call her Sally, and Sally wants to find out some information about Happy Dog on the west side. It's a good hot dog shop if you haven't been there yet. So the web server gets a request to get some information about Happy Dog, and it asks one of its replicas that it knows how to hit. What are some reviews on Happy Dog? What are some pictures? Give me some information about Happy Dog. The replica obliges. We've got a picture of some tasty hot dogs and tater tots. Send it back to Sally. Everything's good. But let's say Sally was just at Happy Dog and wants to write a review. So she posts her review. She thinks it was great. Sends it to a web server. Web server takes the review, maybe does some processing, and decides to hit the master because it knows that it has to do a write. It needs to insert this review into the database. So after we post our review, we'll have the web application typically will redirect you to the business page, for example. So immediately after you do your post request via HTTP, you have to go and do a get, which is you're essentially going to try to read the same data back from the database. And it's entirely possible that this insert in the replication stream hasn't actually replicated to the replica, which we're going to hit because we read from replicas and write to the master. So we still get pictures of hot dogs and tater tots, but we don't get Sally's review, which confuses Sally. if you go and we don't pay Sally for reviews. Sally decided to contribute this review out of her own goodwill. And to see that maybe we swallowed her content or it's being lost is really demoralizing. I've had experiences like that on the web, and I'm sure probably quite a few of you guys have as well. So that's bad. So how can we achieve consistency in a system like this? I mean, so like I've been saying, writes always hit the master. Reads can use either the master or the slave. The majority of reads can use the slave, but sometimes you care about hitting the master for consistency's sake. So in the previous example, it would have been great if we had just hit the master for Sally's, for loading the page after Sally had written the review. So the dirty secret here is that consistency doesn't really always matter. If some second user, Bob, came through and wanted to find information about Happy Dog right after Sally wrote her review, unless Sally and Bob are sitting right next to each other, Bob probably doesn't know that Sally wrote a review, and probably doesn't care. Doesn't mind that information is potentially a little bit out of date, but also probably has no idea. And so it's like the question: if a tree falls in the forest and no one's around to hear it, does it really make a sound, right? If the databases aren't consistent, but nobody knows, does anybody care? And the answer is usually no. So basically, you just want to try to achieve consistency when it's expected. Not so much always, but just when you know that it matters to the user. So the way that you can do this is by essentially, once you've done a write to the master, you basically continue to hit the master for some time until you are pretty sure that replication's caught up. So the way that you can do this, you can have your web servers or your load balancer maybe try to maintain some state about you and your connections and say, this person we know that this guy did a write recently and his write probably hasn't caught up in replication, so we'll just continue to redirect them to the master. But that can be kind of expensive and brittle. Keeping that kind of state in web servers would require talking to each other or using some sort of data store, which can become inconsistent. So it's usually best to just put it in the client side. The way we do it at Yelp is we use a dirty session cookie. So you issue a write, we give you back a cookie that says, here's some token that says you can hit the master, and after some X number of seconds. Actually, I got a slide on this. After X number of seconds, we'll just remove the cookie and you continue hitting a read slave because things have probably covered. Yeah.
If something like bad happens on the user side, though, like say they close their browser and log back in, like load it up real fast, and their browser clears cookies when they exit or whatever, and they log back in real fast, and then they can't see the review.
Yeah. So you could achieve inconsistency that way. But the reality is that by the time the users quit their browser and opened it again and cleared their cookies and whatever else is required to sort of eliminate that state, replication will probably have caught up.
Do you know how long replication takes, or?
Yeah, so it can depend. In a single data center example like we've been doing so far, it's typically pretty quick, on the order of a second or two at the worst. So you could achieve inconsistency, but if the user's jumping through that many hoops to get there,
Okay.
you can't really do much about it, right? So.
So you say the cookie just contains the timestamp when it, expires.
Yeah.
So do you actually set the timestamp dynamically based on current load and because you don't want it to expire before obviously the replication happens, right?
So there are a number of ways that you could set the timestamp in the cookie. You could try to be smart and sort of guesstimate based on load. You can actually monitor the replication stream and figure out how far behind things are, and then basically say, if I know that replication is behind by 2 seconds right now, I'll give you this cookie for 2 seconds plus a fudge factor, plus another couple seconds, and then you'll go back to the read slaves. But in practice, if you've got read-heavy traffic and not that many writes, it's easy enough to just say 30 seconds in the future. If replication hasn't caught up in 30 seconds, then I've got bigger problems. It's easy, requires less engineering effort. So yeah.
So from the security side, how do you prevent a user from, say, creating their own cookie and then launching like 50 million machines at you to take down your master?
Yeah, so that's a good question, and that's I mean, if you don't have a secure system, that's definitely doable. But in practice, it would take like a big concerted effort, and it would to take down our master with a. So you could introduce a lot of load that way, but the easiest way to do that would be to introduce a lot of read load, which typically isn't as problematic for the master database as like a lot of really naughty sort of write load.
Okay.
And you could generate that write load, but you would probably at that point also be having to bypass captchas and stuff like that. The same sort of automated spam stuff. But I mean, the simple answer is basically just to not put it in a cookie, or like to use a cookie for something else. If you do sort of server-side session kind of information, then you can keep that information in a server-side data store, which is separate from your actual data store. Maybe one that can be strongly consistent because it has less traffic, and then you circumvent the problem basically.
Okay.
So,
Also, the cookies could be validated.
yeah,
Inside the cookies.
Yeah. Cool. So another trick that we use on the back end is caches. So widely regarded as like the fastest thing since sliced bread. People often treat it as kind of a drop-in performance enhancement. If you've taken operating systems or computer architecture, you know that caches are basically everywhere in computers, and websites are not an exception. But caches are, even though they seem like you can just sort of drop it in and all of a sudden things will go faster, they can be really hard to get right. And they also make it easy to mask performance and reliability implications. So let's talk about like types of caches. They can sort of, if this is sort of a typical load balancer web database stack, simplified version of Yelp, where can caches go? So you could put in an HTTP cache, something like Varnish or Squid, which basically knows how to respond to HTTP connections and has cache responses. This is great for static websites or dynamic websites, which don't really change a lot because you don't have to keep invalidating the cache. If you don't have a lot of content to sort of to recompute every time, this is super fast. Varnish and other HTTP caches have gotten really good at being really fast. But they're not really appropriate for a website like Yelp. So what are some other options? You could use in-memory caches. You could memoize results of maybe like expensive functions or even database queries. These are typically in the memory on a web server itself. So this isn't like a shared data store. Each web only can benefit from things that it has computed before. And this is useful for some sorts of things, like if you've got some data that needs to be computed once, but then you can sort of keep for the lifetime of that node, this is sort of a good option. But we don't really use this very much at Yelp because we don't have a lot of data that fits that use case. So we use what's probably the most popular option here, which is just regular old memcache, which is essentially you set up some servers that have a lot of memory, and you have them run memcache, and memcache knows how to essentially allocate big slabs of memory, and then lets you treat it sort of as a key value store. That simplifies it a little bit, but and it lets you compute things. It lets you sort of store computed results. So the idea here is that you can, if you've got database rows that are frequently accessed from a database, you can pull it out from the database and then store it in memcache, so that next time you do it, you don't need to do some kind of expensive query. People like to put all sorts of weird things in memcache, like gzipped blobs, even like serialized data structures. Advantages of caches: they're really fast. If you do a complex database query, it can take hundreds of milliseconds. But if you only have to do it once, or once-ish, and then put it in memcache, the round trip to get to memcache is network latency basically, at worst, a couple milliseconds. And misses are really cheap. The cost of doing a memcache lookup that's a miss is only 2 or 3 milliseconds, and you probably still have to go and do this hundreds of milliseconds query anyway, so there's really not a huge disadvantage to looking up stuff that has lots of misses. But it also presents lots of pitfalls. A lot of cache libraries, especially in dynamic languages, make it really easy to cache a lot of really weird things.